So hello friends, in today's video we are going to discuss about the OSNR optical signal to noise ratio. So OSNR optical signal to noise ratio is a very important parameter which must be considered while designing the DWDM link. OSNR is also very important parameter which needs to be keep in mind while designing the DWDM link in terms of performance. It affects the performance of the signal. And OSNR is also a very important parameter which controls the number of optical amplifier in the DWDM system. So let's see what is the optical signal to noise ratio, how it is calculated, and what is the benefit of OSNR, and what is the OSNR, how the OSNR can be improved. So we will discuss all these things in today's video. So let's see the calculation of OSNR in dB by this formula 10 log 10 P signal by P noise. So this is the signal power, this is the noise power. OSNR is dB equal to signal power in dB minus noise power in dB. So suppose we have the we have a signal power for a particular lambda and a noise power for the particular lambda. So OSNR in dB calculated by this formula, signal power in dB minus noise power in dB. So here, this is very important term that the OSNR is always calculated for a particular lambda for a particular channel. Means per channel OSNR is calculated. Optical signal to noise ratio is used to quantify the degree of optical noise interference. Means what is the optical noise interference for of an optical signal in the transmission media, that is calculated by the OSNR. Or you can say this degree of optical noise interference is told by optical signal to noise ratio. It is the ratio of service signal power to the noise power within a valid bandwidth. So you can see here, this is the another formula. OSNR in dB is equal to 10 log Pi divided by Ni plus 10 log Bm divided by Br. So let's see what is these parameters. Pi is equal to signal power on the I channel. As I have already told that the OSNR is calculated for a particular channel. So this Pi is equal to signal power for the I channel. This Bm is equal to equivalent noise bandwidth. This Ni is equal to noise power introduced within the Bm, and Br is equal to the reference optical bandwidth, which is usually 0.1 nanometer, and it is independent of optical modulation, which optical modulation is used, what type of receiver is, and whatever the frequency for which OSNR is calculated. So this is independent of all three parameters. We will discuss in details in the next slide. So here these are the parameters. So let's see. There are some important points about the OSNR. Let's see. Optical signal to noise ratio is used to quantify degree of optical noise interference on optical signal. It is the ratio of service signal power to noise power within a valid bandwidth. So whenever the signal is amplified by the optical amplifier like EDFA, it is optical signal to noise ratio is reduced. Means OSNR is reduced. Why? This is reduced when it is passing to the optical amplifier. So whenever any particular lambda is passing to the optical amplifier, its signal strength is amplified as well as its noise is also amplified. So the output of the amplifier in the result of reduced OSNR. So suppose there are multiple devices connected in the cascaded. So whenever the signal is passing to the next amplifier, the OSNR value of its current amplifier is less than the previous amplifier. We will discuss this point also in further slides. So the OSNR value that matters the most are at the receiver. So the OSNR value, the importance of the OSNR value is at the receiver. So what is the OSNR value at particular amplifier is not as much as important, but at the receiver it is very important. For at the receiver, a particular amount of OSNR must be received for the proper error-free transmission. If the valid OSNR is not get or not received at the receiver, it will result in errored transmission, or you can say the degraded signal. We will discuss this point also. So the OSNR limit is one of the key parameters that determine how far a wavelength can travel prior to regeneration. It means the OSNR is the parameter which determine means how far a wavelength can travel without a regeneration. This is the parameter which limits. Means it is not possible that for a particular span we are introducing number of optical amplifier and it can go to the very far distance. No, it's not possible. This is the OSNR which limits the distance. So OSNR serves as a benchmark indicator for the assessment of the performance of optical transmission system. DWDM network need to operate above the OSNR limit to ensure error free, which I have told in this. At the receiver, the OSNR value is very important. there is a relationship between BR and the OSNR. You can see here, this is locked in BR is equal to 10.7 minus 1.45 and OSNR in dB. Optical signal to noise ratio. Let's discuss some other very important points about the OSNR. So whenever the OSNR is used, it means the OSNR for a particular lambda. I have told already that OSNR is calculated per channel. OSNR is the ratio between the signal power and the noise power in a given bandwidth. Most commonly, a reference bandwidth of zero point 0.1 nanometer is used, and this bandwidth is independent of the modulation format, the frequency, and the receiver. It means for this amount is set for all the frequencies, for all the lambda, or for all the light pulse. This is independent of the modulation format, means it is this common bandwidth, or you can say reference bandwidth is applicable for all types of modulation format and what are all types of the receiver which is used as a receiver. OSNR is measured with the optical spectrum analyzer. So multiple signals or multiple lambda you can say passing through the fiber. So if you want to see what is the OSNR for a particular lambda, or you want to see a OSNR value for all the lambda which is traversing through the fiber, you need a equipment which is known as the optical spectrum analyzer. Signal to noise ratio is measured used in science and engineering that compares the level of design signal to the level of background noise. Signal to noise ratio is defined as the ratio of signal power to the noise power, often expressed in decibel. It means a ratio higher than 1:1, or you can say greater than 0 dB means more signal than the noise. So suppose if a 20 dB OSNR is required at the receiver, it means 20 is the signal power and 1 is the noise power. So greater than 0 dB is meaning that the more signal than the noise. If the ratio of the service signal power to the noise power within valid bandwidth, okay, it is the ratio of service signal power to the noise power. When the signal is amplified by the optical amplifier like alpha, the optical signal to noise ratio is reduced. I have discussed already, like whenever any amplifier is introduced, the signal is passed to that amplifier, and the output of that amplifier, or you can say when all the signal passing through that amplifier, the OSNR of the channel will be decreased. And this is the primary reason to have limited number of optical amplifiers in the network. For terrestrial long-haul light wave system, an OSNR of at least 20 to 25 dB is required to achieve a desired Q factor or error-free transmission. Means this is, you can see, this is the desired value of the OSNR which must be received at the receiver. The minimum required OSNR at the receiver depends on the bit rate. So we will see what is the OSNR value which is required at the receiver when the wavelength had different bit rate. Suppose wavelength has having 2.5 Gbps per second, 2.5 GB per second. So the 20 dB OSNR is required at the receiver, minimum 20 dB. Below that results in the errored signal or degraded signal. So 26 dB minimum OSNR is required if we have the wavelength with a 10 Gbps speed or bitrate. So if a wavelength is traveling to the 40 Gbps, 32 dB minimum OSNR is required at the receiver. Suppose a wavelength is traveling with the 100 Gbps bitrate, so at the receiver 40 dB of OSNR value is required to receive the better signal, the quality signal. If the OSNR value is less than 40 dB for 100 Gbps bitrate signal at the receiver, this results in the degraded performance of that signal. So practical OSNR calculation. So we can see how the OSNR value is actually calculated. So we have discussed this formula. P is equal to signal power, P noise is equal to noise power. You can see SNR and NF calculation. So see, this is the amplifier. This is the input power of the amplifier. This is the input signal power of the amplifier. This is output power of the amplifier. This is signal output of the amplifier. This is the total power. Total power means power of all the signals. And this is for a particular signal. This is signal input signal power for a particular channel. So this is the difference between P and S. Suppose for an amplifier 10 channels is passing. So this signal input power is for a particular channel, and this P is for the total power of that all the channel. So this is the P in, this is the P out, this is SIN, this is SO. You can see here, this is the noise power NI at input. This is the signal power and input. This is noise power at output, or you can say no output noise power. This is the output signal power. Signal to noise ratio at input is equal to signal power at input and noise power at input. Signal to noise ratio at output is equal to signal power at output, noise power at output. And noise power at output can be calculated by signal SIG, means signal at input into gain of the amplifier, and NI means noise power into gain plus NA. This is the noise of amplifier. Because every amplifier has a noise, means that's why whenever the signal is introduced, the noise is added in that signal. You can see here P out is equal to G into P in. This is the gain of the amplifier, and this is the input of the uh, input power. So S out is equal to G into S in. OSNR is equal to P out divided by noise. In dB, 10 log 10 is equal to S by N. S is equal to service signal power, N is equal to noise power, and G is equal to gain of amplifier. Ni is equal to input noise, this one. Si is equal to input signal. Signal to noise ratio at input is equal to signal to noise ratio at input and noise at input. Signal to noise ratio at output is equal to signal to noise ratio at output, signal at output, noise at output. Na is equal to amplifier noise. You can see here this Na. Noise factor is equal to signal to noise ratio at input divided by signal to noise ratio at output. This is the noise factor, and this noise factor is the property of this amplifier. NO is equal to Ni into gain plus Na. This is NO, output noise power. G is equal to gain of amplifier. Calculation of noise. How the noise power is calculated? Let's see. So noise power of channel. For a particular channel, and noise power is equal to noise figure into H nu into G minus 1 into B naught. So noise figure, you can see here, this is the noise factor. So noise factor is nothing, noise figure is nothing but the noise factor. But when this noise factor is expressed in dB, it is called the noise figure. So you can see here noise figure is simply the noise factor expressed in dB. So this is the noise factor calculation, and when this noise factor is expressed in the dB form, it is called the noise figure. Noise figure of the amplifier expressed in dB. H nu is photon energy at wavelength of interest. H is equal to Planck's constant. V is equal to optical frequency, or you can say particular lambda, particular light pulse. G is equal to gain of amplifier, and BO is equal to optical bandwidth for noise measurement, 0.1 nanometer. So you can see in this formula, this noise figure is fixed, this H is equal to fixed, this nu is equal to fixed, this G is equal to fixed, this B naught is equal to fixed. This noise figure is not fixed, this Planck's constant is fixed. For a particular, if you are calculating the channel power, noise power of particular channel, this nu is fixed, this G is fixed, and this B naught is fixed. So it depends upon the noise figure only. Noise factor of amplifier. How the noise factor is calculated? Noise factor is equal to signal to noise ratio at input by signal to noise ratio at output. Note, signal to noise ratio at input and signal to noise ratio at output is equal to in electrical form. Noise figure factor is equal to 1 plus Na by Nig. Noise figure is equal to noise factor expressed in dB. Noise figure is equal to 10 log 10 signal to noise ratio at input, signal to noise ratio at output. This is a noise figure. This is the characteristics of amplifier. Noise figure is equal to 10 log 10 1 plus Na by N by G. We have just simplified this formula. G is equal to P out by P in, gain of the amplifier, or S out by Sn. So in the formula of noise power, only variable parameter is noise figure. You can see noise figure is the only parameter. Noise figure, signal to noise ratio input and signal to noise ratio output. And you can see this noise figure is equal to 10 log 10 1 plus Na divided by Ni minus G. So input power as noise is fixed, G is fixed, so it depends upon the Na, means amplifier noise. So noise power of the channel mainly depends on the noise figure of the amplifier. This is very important point. In noise figure formula, Na and G is fixed. For any amplifier, we can change in the value by using different amplifier. The only parameter which varies Ni, noise at input. So suppose this Ni passing through this amplifier, and when this Ni out of that amplifier, this will convert into No, N out, No. So this No, you can see here, noise power of the channel depends upon the noise figure, and for next amplifier this will be the Ni. That is the parameter noise for the noise figure, you can see. So for the next amplifier, it will increase the noise power, and that's why the OSNR is keep decreasing whenever the optical amplifier is introduced. So this is all about the calculation. So here we will see OSNR calculation at any stage of transmission path. You can see here, this is the diagram, this is the transmission, this is direction from TX to RX. This is amplifier 1, 2, 3, 4. Here the 4 amplifier is used. This is span 1, this is span 2, span 3, span 4, span 5. So span loss is fixed. I have just keep it span loss is fixed for all the span. This is 23 dB. This is the amplifier 1. G1, G2, G3, G4 are the gain of the amplifier 1, 2, 3, 4. NF1, NF2, NF3, NF4 is the noise figure of amplifier 1, 2, 3, 4. OSNR after amplifier 1 is F1. OSNR after amplifier 2 is F2. OSNR after amplifier 3 is F3, and OSNR after amplifier 4 is F4. So see, OSNR at any stage I can be calculated by OSNR I is equal to P in I NFI H nu into delta F. So let's see what are the parameters. So P in is equal to the input power. You can see it, this is P in 1. NFI means noise figure at any stage. This is H and nu frequency, and this is the reference bandwidth. So these you know all these terms. This is the noise figure. This is fixed. This PEN and noise figure is variable. So if OSNR final at last span is F, suppose at after the last span 1, 2, 3, 4, the OSNR is F. At each stage it is F1, F2, F3, and F4. Then the relationship between overall OSNR and the each stage OSNR is like 1 divided by F is equal to 1 upon F1, 1 upon F2, 1 upon F3, and 1 upon F1. So F1, you can see here OSNR after amplifier 1. After amplifier 1, OSNR is F1, after 2, after 3, after 4. And overall OSNR is calculated by this formula. Now consider G1 is equal to G2 is equal to G3 is equal to G4. Same gain of all alpha. We have considered all the amplifier with the same gain. Means G1 is equal to G2 is equal to G3 is equal to G4. Same type of alpha in the series. Considered each span has a same span loss. Like 23 dB considered in this scenario. Each amplifier has same noise figure. We have calculated, we have assumed that NF1, NF2, NF3, NF4 are the same. Gain equalization is perfect, and OSRB, optical spectrum resolution bandwidth, is 0.1 nanometer or 12.5 gigahertz. So the overall SNR can be represented as OSNR in dB is equal to P out, means P out is equal to transmission. What is the output power from this transmission? Minus L minus NF minus 10 log N plus 58. So this is a standard formula. If we are considering the equalization is perfect, OSRB is 0.1, all the gain of them, gain of all amplifier is same, span of all the span is same, then this formula is considered. P out is equal to output power from the transmitter, L is equal to span loss, N is equal to noise figure, N is equal to total number of span. Okay. So you have seen N is equal to total number of span. Here 1, 2, 3, 4, 5. Total number of span is this noise figure, and L is equal to span loss. This is span loss. We have just considered these all span loss is same. The OSNR at the end of the system determines the Q factor or the BER of the system. At the end means what is the, this is the final OSNR determines what is the Q factor or what is the BER of this system. So this is very important parameter. Overall OSNR represents the quality factor and BER of the system. The minimum OSNR required to achieve a specific BER in a link is a function of the bit rate. Okay, the minimum required OSNR at receiver 20 dB for 2.5 Gbps, 26 dB for this, 32 dB for 40 Gbps, and 40 dB for 100 Gbps. bit rate. So this is all about the calculation, practical calculation of the OSNR. If the gain of the amplifier is different, span loss is different, and transmit power is different, so this formula can be considered to calculate, and OSNR at any stage can be calculated by this formula. So calculate OSNR at each stage and keep in this formula, and you will get the overall performance if this ideal condition is not considered. OSNR calculation practical explanation. Okay, so let's see one example. We have a formula like OSNR dB is equal to P out T minus L minus N F minus 10 log N plus 58. The given values: L is equal to 23 dB, span loss is 23 dB. We have considered that 23 dB is for all. NF is equal to 5 dB. This noise figure for all the amplifier is same, which is 5 dB. N is equal to 4. Total number of spans, you can see 1, 2, 3, 4. PCH is equal to launch power into the first fiber span in dBm from TX. So the overall SNR at the fifth span, this span, is calculated by this formula: PCH minus L minus NF minus 10 log 10 N plus 58. So OSNR dB is equal to 1 minus 23. This PCH means channel power, 1 dBm minus 23 minus 5 noise figure minus 10 log 10 number of spans plus 58. We have just put all these known values in this formula. So OSNR dB is equal to this. OSNR is, we have just simplified this equations, and we are finally getting 24.98 dB. So this is the OSNR, overall OSNR received at receiver. Calculation and relationship of Q factor to the OSNR. The logarithmic value of Q in dB is relation to the OSNR. So what is the relationship between Q dB and OSNR? So Q in dB is equal to OSNR plus 10 log 10 B naught by BC. In this equation, B naught is the optical bandwidth of the end device photodetector, and BC is the electrical bandwidth of the receiver filter. Okay, this B naught and BC is the parameters of the receiver. In other words, Q is somewhat proportional to the OSNR. You can see the Q is proportional to the OSNR. Generally, the noise calculation is performed by the optical spectrum analyzer or sampling oscillation, and these measurements are carried over a particular measuring range of BM. Typically, BM is approximately 0.1 nanometer reference bandwidth, which we have discussed already, or 12.5 gigahertz for a given OSA. Q in dB in terms of OSNR, it can be understood that if BC is greater than B0, then the OSNR dB can be greater than QdB. These features can you can say this conclusion comes from this formula. If BC is greater than B0, means OSNR dB is greater than QdB. For practical design, OSNR must be greater than QdB. Means OSNR in dB must be greater than QdB by at least 1 or 2 dB. For a practical error-free transmission, it is required that the OSNR at dB must be greater than quality factor in dB, and at least by 1 or 2 dB. Means if this Q is around 20, so OSNR must be like 22. Typically, while designing a high bit error system, the margin at the receiver is approximately 2 dB. So this is the margin we keep at the receiver, such as the Q is about 2 dB smaller than the OSNR. So quality factor is 2 dB smaller than the OSNR. We just keep the 2 dB margin. Calculation of BR from the OSNR. You can see here, this is the TX, this is the output power from the TX, this is input power at the receiver. This is NTP, the number of photons launched at the transmission. Delta P is the number of photons lost hypothetically due to attenuation, absorption, scattering, and other impairment during transmission. So we know that in fiber there is a lot of lot of attenuation or impairments occurs when the light pulse or wavelength is traveling to the fiber. So this delta P is the number of lost photon. This NTP is the number of photon launched at the transmitter. So at receiver, NTP minus delta P will get this is a launch and this is a lost. So at the receiver, how much receive? NTP minus delta P, and this is the input power. For most practical WDM networks, the requirement of BR is 10 to power minus 12. So this is the like requirement, you can say, for a practical or for a error-free transmission design. This bit error rate is 10 to power minus 12 or 10 to power minus 9 to 10 to power minus 12, which means that the maximum one out of every 10 to power 12 bits can be corrupted during the transmission. Suppose if 10 to power minus 12 bit are transmitted in the transmission system, then only one bit in 10 to power 12 can be corrupted during the transmission. This is the practical requirement for error-free transmission. Therefore, BER is considered an important figure of merit for WDM network. All design are based on this quality. For a photo detector to detect at a 1 bit correctly, assuming non return to zero or any this type of modulation at the receiver side. Let's consider NP, certain number of photons required falling at receiver. So this is the NP, means this is the required number of photons which must be received at the receiver. NTP is the number of photons launched at the receiver. Delta P is the number of lost photon. Then if NTP minus delta P is less than NP, or you can say NP is greater than this, the receiver will not able to detect the signal properly. To sustain good communication, it is necessary that NTP minus delta P is greater than NP. It means this NP is the certain minimum number of required photon at the receiver. So NTP minus delta P must be greater than NP, means the received number of photon must be greater than the minimum or limitation of photons required over L, the distance of the you can say the communication channel. The number of photons translate to the power of the optical signal. The most harmful effect pulse spreading is in ISI. Even if you assume ISI never to happen due to good decision, due to good design, you can say, still a small amount of dispersion has several harmful effects. The spreading of the pulse power, its power content, which means that delta P increases, means loss of photon will increase. In other words, the number of photons that will strike the detector decreases, you can say, by this effect. If the ASI happens, then this photo detector number of NP, you can say the NP will decrease. Therefore, when we are considered dispersion limited system, we must consider a power penalty due to dispersion. This power penalty can qualitatively be defined as the net loss in power because of dispersion during transmission of signal in a dispersion affected limited system. Qualitatively, power penalty can also be considered the next extra power required to pump up the signal so that it reaches the receiver. This is the power penalty. This is very important features. This is very important consideration. This is very important point. To recover from the dispersion, this power penalty must be added. Typically, the power penalty for most network is in the range of 2 to 3 dB. ITU specification G957 state that this penalty should not be greater than 2 dB. So this is 2 to 3 dB is power penalty is considered, but as per ITU, it should not be greater than 2 dB. Means we must design such a network in which the power penalty greater than 2 dB is not required. BER is equal to 1 upon 2 ERFC 0 by under 2, where QDB is equal to OSNR 10 log 10 B naught by BC, which we have seen in previous. Okay, so let's see how the BER is calculated by OSNR. So before that, we must consider some points, very important points. So whenever the optical signal or light pulse is passing through the transmission fiber, optical signal suffers more than only attenuation. So means optical signal is not affected only by attenuation, but it affects more by amplitude, spectrally, temporally signal interaction with light matter light, leads to other signal disturbance such as power reduction, dispersion, polarization, and unbalanced amplification. So there are several factors which affect the light when it travels through the transmission medium, more than that of attenuation, thus leading to random noise which causes misalignment. Jitter means all these scenario create the random noise which causes misalignment, jitter, and other disturbance, resulting in erroneous bit, means bit will more bit will be in error. the rate of which is known as a bit error rate. So by these effects, by these you can say linear effect or nonlinear effect occurring in the fiber medium, that affects all this property and create the random noise, which increase the bit error rate, is ultimately indicator for measuring transmission quality, and thus the transmission quality will be decreased due to the impact of the factors such as noise, nonlinear effect at dispersion, PMD, polarization mode dispersion, chromatic dispersion. The waveform of optical signal coupled into the fibers will be distorted, and these optical signals, the waveform of that optical signal is not received at the receiver in the same form on which it is transmitted. Because of all possible influences outlined, bits transmitted by source and bits arriving at the receiver may not have the same value. Means whatever the bits is transmitted from the transmitter, it not received all good by the receiver. Some bits will be in error. In actually a threshold value set at the receiver. Above the threshold refer to a logic 1 and below threshold logic 0. Means on the receiver we have said that this amount of errored bit can be considered. Above that it will raise a alarm, or you can say it will declare that the signal is degraded, means more errored bit is receiving at the receiver. BER is equal to number of incorrect received bit by number of transmitted bit. This is the bit error rate, you can say number of incorrected received bit and number of transmitted bit. In order to measure BER in photonic region, the optical signal is converted to electrical signal. Assuming a confidence level of 90%, BER threshold is set to 10 to power minus 10, and a bit rate of 2.5 GHz. The required number n is 6.64 into 10 to power minus 10 given in the OSNR. The empirical formula calculated BER of signal fiber is, suppose log 10 BER is equal to 10.7 minus 1.45 and into OSNR in dB. Suppose we can understand it by an example. We have a given signal with OSNR 14.5 dB. So calculation of BR is equal to like this. By keeping the values in this formula, we can see that the log 10 BR is equal to 10.30, or you can say BR is equal to 10 to power minus 10 minus 10.30. So this is the bit error rate we can calculate it by the OSNR by this formula. And this is a very important bit error rate is a very important parameter to define the performance or the quality of the transmission system. So impact of amplifiers on OSNR in the optical lengths. We have already discussed, so we will just go through this. So what is the impact of the amplifier on the OSNR? So as we introduced amplifier in the optical link in the OSNR, values decreases as every introduction of new amplifier. So you can see this is the amplifier, and OSNR on this amplifier is 30 dB, and whenever the new amplifier introduced, the OSNR is at this is 29.0, when and the next OSNR next amplifier the OSNR is 27. So OSNR is keep decreasing whenever there is a new amplifier is added. You can say the output of any amplifier has low SNR as the OSNR of output of previous amplifier. You can see the output of any amplifier has a low SNR 20.9, 29.0, then the OSNR of output of its previous amplifier. Here is 30, here is 29. So this is the statement. So OSNR plays a very important role in design of DWDM network. The OSNR put limit on number of cascaded amplifier in the DWDM spans. So the question comes in the mind means in the spans we can add it, we can keep added the amplifier and take the wavelength to the very far distance, but it is not possible, and that is why, because of this OSNR, because of this concept. So OSNR improvement. So how the OSNR can be improvement? So OSNR can be improved by the Raman amplification. OSNR is continuously degraded with the transmission length and ASC. So this degradation can be leached somewhat by distributed Raman amplifier as by using Raman. So let's see how it is calculated. By using Raman, intrinsic noise is produced, which is less effective than alpha. So you can see here the how the Raman amplification improved OSNR, because Raman has intrinsic noise while alpha has AC noise. And you can see, if you remember, you can see that the noise figure depends on the noise of the amplifier. So only that parameters is very important. and that is the benefit of the Raman amplification. So you can say OSNR can be calculated at any stage when alpha is connected in series P in by NFI H nu into delta F. OSNR can be calculated at each stage when the DRA distributed Raman amplifier is connected is in series as OSNR is equal to P in NFI H nu delta F into GRA. So you can see here this the OSNR value is just multiplied by this GRA means gain of the Raman amplifier, and that's the beauty of the Raman amplifier. The factor GRA is in the numerator and hence the OSNR of the system. Means OSNR is improved by this value, gain of Raman amplifier. NFI is equal to noise figure of stage, H is equal to Planck's constant, we have discussed, V is equal to optical frequency, and delta F is the bandwidth of the piezometer of NF. It is basically the zero point 0.1 nanometer or 12.5 gigahertz. Benefit and importance of OSNR. So OSNR stands for optical signal to noise ratio. It is very important parameter to estimate the performance of optical network. It is used in BER calculation of optical system. Q and the BR can be calculated and we know the OSNR and the bandwidth. OSNR is important because it suggests a degree of impairment which is the optical signal is carried by an optical transmission system. That includes optical amplifier. It can be seen as the QS at the physical layer of the optical network. OSNR is directly related to high bit error rate, which will lead to packet losses seen by higher layers. OSNR indirectly reflects BER and can providing a warning of the potential BR deterioration. OSNR has long been recognized as a key performance indicator for amplifier high-speed transmission network to ensure network performance and reliability, and it's related to many design parameters such as number of repeaters, amplifiers, reach, available modulation formats, etc. OSNR improvement tips. So you can see high quality fiber. If you are using high quality fiber, OSNR can be improved. First 2-3 alpha with low noise figure and high input power. ADFA plus Raman in cascaded system. OSNR is improved by the multiplication of Raman gauge. So it is used in the OSNR limited system for the longest span and for the system having much attenuation in the error. This system is costly, so limited. The overall result is improvement of OSNR and zero noise figure. Reduction in BER by advanced coding. You can reduce this BER. So OSNR is improved and FER. So this is all about the OSNR. So we have discussed all these things about the OSNR in details. Thank you.